So where we left off was talking about spanner. So let's start by recapping that. So spanner gives you globally consistent reads via true time, but how does it handle writes that are touching multiple shards? Because remember, spanner was a sharded database. It wasn't a single coherent image. So this is going to lead into what we're going to talk about today. So just take 2 minutes and do that, please. All right, so what did you come up with? I didn't hear a lot of talking, so maybe you guys weren't doing it, but you still ask the question. What do they do about rights?
We talked about they use 2PC to make them.
Right. That is in fact exactly what they did. They implemented two-phase commit on top in order to do updates that were consistent. And I specifically talked about the fact that you need to use two-phase commit because you're not doing replication anymore. What you're doing is these are disjoint data sets and they need to be changed atomically. So you have to have both or neither. So in fact, what spanner actually does is it combines both Paxos for replication using a multi-Paxos log, but across the shards we can't do that because they're not identical. So we're going to talk about when do you use two-phase commit versus when do you use a replication protocol like Paxos. So if you have your data sharded across 5 machines and a transaction that touches 3 of those shards, how do you make it atomic? And you just mentioned it. You pulled it right out. You use two-phase commit. That was the whole reason that we talked about two-phase commit at the very beginning was two-phase commit is what you need to use when you're making changes that are on dissimilar data sets, but that have to be done atomically. So in this case, atomic means all 3 shards commit or none of them commit. And then again, remember that what we talk about when we say commit here is what is externally visible. What's going on under the covers, that's the part that we're taking care of. The external visibility, that is people who are building apps on top of your service, expect that they're going to see a consistent view of the data. So if you're sitting there building the last DS Labs project and you're building the movement of data between shards, you need two-phase commit in order to make sure that the data is correct. And those aren't short transactions potentially. They could be quite long because the database that you're moving, or the pieces of the database that you're moving around, can actually be large. And in many cases, we think of these very small time intervals as essentially instantaneous. But in the real world, we have things that occur that are not instantaneous. Why would you shard a database? I did mention this before. So a single machine database is actually simple. You only have a single log, so you only need one lock manager to deal with mutating different tables within a database, for example. You don't really need a whole lot of complexity there. You need that complexity when you decide you're going to start scaling. Now, one way to scale this is vertical scaling. Let's go buy a $45 million computer instead of a $500,000 computer. And cost doesn't increase linearly. So when you buy a cheap computer, it might be $100. But that's very high. When you want something that is twice as powerful, you're not going to pay twice the price. You're going to pay probably closer to 4 times the price. When you go from a system that has 128 cores to a system that has 1,024 cores, so there's 8x as many cores, it's not an 8x increase in price. It's probably more like a 64x increase in price. Yeah, it's pretty amazing when you start looking at that, what happens as you scale up. If you decide you want to go buy an NVIDIA H300, you're going to find it costs just a little bit more than that 5090 that you were having your eye on. It's got a lot more memory. It's got a lot more processing power. You'll probably need to have an electrician come in and install an outlet for it, and a lot of air conditioning for it because it generates a lot of heat. But, so you're living in the wrong part of Canada for that. You need to go someplace that's really cold and you live next to a hydro plant so that you can just tap it. That's the reason that we don't do vertical scaling without limit. Same reason we don't build really tall buildings. It eventually just doesn't work very well. So the alternative to this is that we build horizontal systems. We spread out. But now we move this from a hardware problem to a software problem. If we can solve the problem with software, though, we have better scaling. And that's why we build systems like Paxos. That's why we shard our databases, because now all of a sudden I can literally build a database that just takes a bunch of workstation class machines and provides massive scaling. I've worked with a company that does that, called Teradata, that brilliant people, seriously some of the smartest people I've ever worked with, and that was all they did. They spent all of their time making a scalable database that could do massive queries really fast. And that was not a cheap database, but now the money is going into the software, not the hardware. And now you can also build things like reliability, because frankly, building a $64 million computer that's hardware fault tolerant is a lot more expensive than building a network of cheap computers that are software fault tolerant. But both of them still exist in the real world. There's a company called HPE, Hewlett Packard Enterprise, that is largely consisting of a group of people who built what was called nonstop computers. I think they got started in the late 70s or early 80s. And they got bought out by Hewlett Packard in the 1990s. And I worked with those people as well. And they did hardware fault tolerance. And the people who paid the big bucks for those machines were people who said, we can't allow this horizontally scale thing. Notice they're vertically scaling, but in a horizontal package. We can't allow things to fail. They worked in markets where downtime was often measured in hundreds of thousands of dollars an hour. One of the customers I worked with at one point, I think it was Lehman Brothers. That's a long time ago because that's before they disappeared in 2008. One of their primary businesses was trading U.S. Treasuries, and if they were down for more than 4 hours, they had an obligation. They had to actually call the U.S. Secretary of the Treasury and tell him they were down because it would affect the liquidity of the market. It was that kind of serious. They spent a lot of money on their computers. They spent a lot of time and money. So the reason that this is a real problem space is because the problems we are solving are really hard, and they matter to people who happen to have very deep pockets. And the fact that the problems are hard and fun to work on is just icing on the cake. Because they are fun to work on. Well, maybe. Is anybody having fun working on these problems? They kind of screw with your head a little bit. In a good way. In the way that it's like you have to think about the world differently than you do when you just assume everything, there's such a global clock and everything happens instantaneously. The cross-sharding problem is very real. If we split our database up so that we have accounts in different regions, different ranges, and this is just a single bank, but it's transferring money between two different accounts that are in different shards, we have to do that transactionally. Because if we don't, we might take the money out but not put it in. It's the ATM problem all over again. And you will notice this is a pattern. Most of the problems that people are willing to spend this kind of money on happen to involve moving money, handling things that have financial or economic value. So the question now is, what makes cross-shard transactions harder than single-shard transactions? This is sort of revisiting what we talked about before. When we start doing two-phase commit over the network, what makes it hard? So take 2 minutes, talk to each other about it, and see what you can come up with. All right, so what did you come up with? Why is it harder to do a multi-shard transaction than a single shard transaction? This wasn't even meant to be heavy lift. Maybe it is.
Well, it's harder because we need to coordinate multiple nodes, but assuming the reason 2PC, like you just said, which its whole thing is to ensure atomicity, so we're using it properly. I can't think of specific failures somehow.
You can't think of what could go wrong when you have two parties involved instead of one?
But assuming we're properly using 2PC,
You hand waved the problem away. So the problem is that 2PC itself is actually harder to implement than a single node, right? All right, I'm going to bring bribes out now. So you got one for answering, and you can have one. So, what failure would violate atomicity? So, I think this is kind of an interesting reframing because we haven't really talked about it this way in the past, which is we're separating the decision from the execution. But that is, in fact, exactly what we do. That's what Paxos does. Learners are the executors. Deciders are the proposers and the acceptors, technically the acceptors. In phase one, the coordinator asks each of the participants, can you commit? Each participant acquires whatever locks they need to make sure that they can maintain durable state or consistent state. Nobody else can see anything while they're changing it. They record their promises to a durable log, and then the participants vote, yes or no. During the commit or abort decision, everyone has to vote yes, and then the coordinator sends a commit. If anybody votes no, or they time out, the coordinator sends an abort. The participants then execute the decision. So this is the happy path. We start here. We have our coordinator sends out prepare messages to both of the shards. The shards both say, yeah, I'm ready. I got everything. I'm prepared. And then the coordinator says, okay, you're done. Commit. That's all it takes. But what could possibly go wrong here? Well, maybe the second shard goes down, or it says no for some reason because it can't get the lock very well. It has a lock. Something went wrong. It no longer can commit. Well, in that case, we do an abort. That's fine, because two-phase commit is a unanimous consent protocol. Well, that's where we started 10 lessons ago. What is that, 5 weeks ago? That's where we were. The coordinator proposes, the participant votes. Now I'm using terminology that we introduced in Paxos, proposes. But that's in fact exactly what we're going to end up seeing, is that these are not radically different, but they're somewhat different. So an ignore, timeout means an abort. We remember when we went to Paxos, we used unanimity for consensus, using the quorum intersection property, but we don't have a quorum intersect here, right? You don't know what values I'm changing, I don't know what values you're changing, but we still need to have that coordination. So that's that's why we can't actually do Paxos here. That's why we actually need two-phase commit, because we're not manipulating the same data. We're manipulating different data that happens to be entangled in some way. So it's relational, and we have to maintain that relationship. But what happens when the coordinator dies? That's what led us to three-phase commit, which was kind of an awkward sort of let's try and recover by voting on a successor model. So these two have both said yes to the prepare, but they're holding those locks. Now they have to wait until the coordinator recovers. That's actually the reason that two-phase commit becomes difficult to scale properly. It's that you have to hold the locks until you know what the outcome was. Because neither shard A nor shard B know what the outcome is until the coordinator tells them what it is. In Paxos, we had a recovery protocol. We had a mechanism for doing that, for fixing that. So this is essentially a make no forward progress. This is correctness over availability. People can still read the old values because that's perfectly allowable in the two-phase commit protocol. You can keep seeing what the data was before we started the operation because that's a consistent view. But they can't move forward from that. It is literally a fundamental property of having this kind of consent model. I thought this was an interesting way of framing it. Since we've now gone down the Paxos road, two-phase commit is basically what you get if you only have a single acceptor. Oh, yeah, that's kind of cool, isn't it? So in order to get a quorum, I have to get one acceptor. But that's exactly what it is. So now we actually have a way of arguing that this is kind of like Paxos. But not the same. So in two-phase commit, what we're doing is we have a coordinator, and the coordinator is the one who makes the final decision. Here, the decision is made by all of the acceptors, all one of them. Therefore, we have the coordinator be the decider. And this is safety via unanimous vote. Here, we can actually tolerate a number of crashes because we only need a quorum. But when you make your quorum one, you've converted democracy into a dictatorship. That's what you get. So there's no fault tolerance here. So here's the interesting question. What's structurally different here? How could we get better properties from our two-phase commit protocol? Could we get the same kinds of recoverability that we had with Paxos? Take 2 minutes. See what you can come up with. Oh, and only one cookie per person. Unless nobody else wants to answer, in which case, then I have a lot of cookies. I brought several dozen. Actually looking at the slides. Wow. I didn't add some polymarket. I've never been to polymarket. I've never looked at making a polymarket. I only talked about it around my phone. And guess what? I get hats. But I shouldn't believe that they're monitored. Right? They really think we're stupid. We would never do that.
Can't do anything.
Sorry.
They just know we can't do anything about it. Like,
Actually, I had that argument very recently, yes. With ChatGPT. It's kind of like, you want to be able to use the phone that you just bought. And the first thing they do is they give you a 40-page legal agreement you have to agree to. And it's like, well, what am I supposed to do? Take the phone back? Which they will let you do. But what do you do 2 years later when they tell you that if you don't upgrade your phone, you don't update the software on your phone, it's going to stop working? Yeah, that's kind of a sort of sleazy. It's a reality of the business world. So you agree to it anyway, because you don't really have any choice. It's called a Hobbes bargain, I think is what it is, by the guy who actually talked about this. Sorry? Yeah, I don't think it was Calvin and Hobbes. So, yes. So literally, when you're given a choice that isn't really a choice, and we get those all the time. All right. So, what did you come up with? The cookies worked. Okay.
In Paxos, there is at least one node in a quorum that will know the very up-to-date state, and then it can probably take over when a particular proposal crashes. In 2PC, there is no provision of that particular. So if the proposal crashes, it crashes.
Right. Problem is that our quorum here is the coordinator. So if the coordinator's down, just like if we didn't have a quorum in Paxos, we wouldn't be able to figure out what the decision was. Do you see an escape here yet? I'm not going to do this as groups. This is kind of dumb. I think we've got the point. I mean, it is interesting. You can go through this process of drawing it out and saying, here's what's actually happening. But the recovery isn't actually very easy. So I think this piece of it here is kind of useful. So how can you recover from this? And the answer is you really can't. Not based upon what we have with two-phase commit. So, can you see a solution that might work here yet? What's the fundamental weakness we have right now in two-phase commit? What piece is it that when it breaks, the system is stuck? Right, the coordinator. So how can we make the coordinator more resilient? What is the coordinator doing?
It's proposing a single view.
Right. Commit or not commit. Great. And what do we have that will actually solve the single value proposer problem that is in fact fault tolerant? There you go. Gee. So how about if we actually replicate our coordinator? Now, if we really want to make our coordinator have more state, then we can just simply replicate the state as well. It's fine. Then we just put multi-Paxos underneath our coordinator. It looks like a single coordinator to the rest of the system, but underneath the covers, what we have is multiple coordinators. This is the same thing that happens when we do our view server in the primary backup replication. The view server is, in fact, the coordinator in that instance. It's a weak spot. So we can replicate it. Problem solved. Now we actually have a way of being more resilient in the face of failures. So, I mean, this just walks through the whole analysis of why you can't solve this in the two-phase commit problem. So instead of accepting that the coordinator goes away, you say, well, we'll just make the coordinator more resilient. We'll create the ability to survive a certain class of failures. So in Paxos, when a proposer crashes in that phase 2, what happens is a new proposer comes out, runs a ballot protocol, this is multi-Paxos, runs a ballot protocol and gets a quorum, and part of getting that quorum, if you actually look at the multi-Paxos protocol, is what was the last decision that was accepted by anyone under the previous leader. It's literally part of the protocol. And so now it knows what the last decision was, and the new leader knows, this is what I know about, this is what someone knew about, that's the last accepted proposal. Doesn't mean that it was adopted, it means it was accepted by someone. And that region between last accepted proposal that we can see and what's in my database as the new leader, that's the region I have to recover. Because if I don't have that state, I need to know what happened in there. And the way I fix that then is not defined by Paxos. It's defined by your recovery protocol. Paxos gives you everything you need to figure out what you have to get, but doesn't define how you get it. But now you actually know what you need. And you can go ask other parties, other nodes in the system. You can say, I need this stuff from you. And that it just reads. You're reading those things. And you can see what actually happened. And that's part of what you do when you build an actual working distributed system. That's why I say, start from the failure. What do I need to know? In this particular case, what I did was I did the opposite approach, which is I said, okay, new leader, what does he need to know? He needs to know what the in-flight region was. You get to go and build the implementation that grabs that from wherever you can get it from, restores it, and now the new leader is prepared and ready to go. My extreme example of this is a machine goes down. It requires new storage device. New storage is installed. We bring the machine back up. It's part of the Paxos group there. It comes up. It has a completely empty database, and it can't find the leader, so it calls a leader election, and it wins. This is beautiful, right? It wins, and it literally then says, okay, yikes. So I haven't ever seen anything, and you tell me that leader 42 just sent out decision 1096. Okay, well, let's start figuring out what's in that region. And interestingly enough, knowing what the bounds of that region are becomes part of defining when you can clean up your log of decisions. The Paxos DS Labs, which is based on Paxos made moderately complex, is mostly about the thing that makes the actual implementation really complicated is knowing when the log itself can be compacted. Knowing when everyone already knows everything so we can't end up in the situation I just described. And that's essentially what they're saying, is that that particular situation is one they no longer address because they aren't keeping the infinite history that would be required otherwise. I think that's perfectly reasonable. Don't bring up an empty database and expect that it's immediately going to get pull all the data in. But this gives you the more realistic scenario, which is a new leader might be behind because they were in a partition. The partition is repaired. The new leader, the node doesn't know who's the leader right now, so they call a leader election because they're allowed to do that. They become the new leader. Now they have to catch up. But it works right. Eventually, the new leader catches up. It can now move forward and make new proposals. Generally, what happens in implementations is the new leader will get what is in the in-flight region and then repropose it. And if it reproposes it and it gets a quorum, that means it wasn't previously adopted. Because otherwise it would get a conflict. It wouldn't get a quorum. They wouldn't vote for it under the old ballot number. I'm glossing over details there. I will leave it there. You can make that work, right? It's a fun part of building a Paxos. Okay, so Paxos replicates decisions. Two-phase commit doesn't replicate those decisions because there's no higher ballot in 2PC. There's no quorum of coordinators unless we build one that's invisible. Because it's not actually part of the protocol. So what ends up happening in Spanner is they have a 2PC coordinator, Each of the shards is in fact a Paxos group. Oh, and then they used Paxos on the two-phase commit coordinator so that they have resilience there as well. And that was their solution. And it actually makes a lot of sense. So 2PC provides the atomicity you need, Paxos provides the fault tolerance you need, and by combining these two things together, you end up with something that's really pretty interesting, which is both providing you strong atomic guarantees across multiple different data stores at the same time that it is in fact fault tolerant. We're just stacking turtles. This one's a green turtle, this is a yellow turtle, we put another green turtle on top of that, but they're still turtles. We're just using these techniques in a way that satisfies the particular problem we're trying to solve. Now, at high level, that doesn't sound very hard. I can tell you that when you actually build these things and implement them, the first time you do this, you'll find that it performs like a sleeping dog. It's there, it moves occasionally. You know it's not quite dead, but it's not exactly moving at the speed of a not sleeping dog. So you're going to spend a lot of your time actually making it run faster, work better. You're going to look at how do I optimize this, how do I squeeze the messages down, how do I spend less time waiting for messages to arrive, and that's where it will get fun. You can spend a lot of time trying to optimize these systems to make them work right. So what we ended up with now is in a shard we use multi-Paxos, which we've already talked about. Across shards we use two-phase commit, which we've already talked about. The coordinator we make survivable by building a replicated Paxos, and we can actually make the participants, the individual shards, resilient as well, because we're using Paxos. We can replicate prepared state even. So we can literally build 2PC on top of Paxos on top of, with 2PC on top of it. And then we'll put Paxos in there just to make it really interesting. The nice thing about this is that the blocking problem of 2PC that we sort of tried to address with 3PC. 3PC you won't see a lot because it's sort of complicated and it still doesn't really solve the underlying problem. Paxos does a better job of solving the underlying problem. So that's why you'll see Paxos and 2PC intermixed with each other. All right, so now, 2PC blocks because the coordinator is a single point of failure. Spanner replicates the coordinator with Paxos. Does Spanner's 2PC still block? If so, under what conditions will it block? This time I'll give you 3 minutes. All right. So what did you come up with? Who wants a cookie?
Yeah, it still blocks if you allow a reach from another form in the Paxos cluster or the gradient.
Right, it's still gonna block if you can't reach quorum, right? So it's not that this is completely without any problems, but at least it's reduced that. So I think that one of the important points to take away from that is we can make the problem better, but we can't fix everything. When everything falls apart, we're kind of stuck. In Spanner, they allowed the transactions to actually execute and then they coordinated the commit, which is an interesting decision. So they said, we want to allow writes to continue moving forward, but we'll deal with the things that can go wrong at the end. Which, okay. In Calvin, which is a different system, similar but different system, what they decided to do instead is to decide on the order in which things were going to happen. They're linearizing the order of events. This is very Paxos-ish. So they had a global sequencer that actually assigns a total order to all the transactions. Every shard then receives an ordered log of those transactions. Each shard executes the transactions in that order in a deterministic fashion. So in other words, you know that this is what's called a replicated state machine. What you know is, because it's a state machine, you know when it gets that, you know exactly what it's going to do. It's deterministic. There's no stochastic variation. Because if you start getting stochastic variation, it's going to get a lot harder. You're not going to be able to use this trick. So here, we have the global sequencer. Every shard receives the ordered log of transactions. Every shard executes the transactions in order. They don't need any 2PC at all. Because now what they're doing is they're actually coordinating the order in which the changes apply to this distributed log. I give you a set of instructions. You follow the set of instructions. You end up getting the same thing that he gets when he follows a set of instructions, or what she gets when she follows a set of instructions. Because you all are implementing exactly the same state machine. So what are the trade-offs? This is where things get really interesting when you build distributed systems. It's not that there is any one correct solution. There are almost always pros and cons, and there are going to be situations where what you're building makes trade-offs that don't look like what anybody else decides, because you're solving a specific or particular problem. This is how I end up with a Martian data center that has very interesting characteristics, because I said this is the problem I wanted to solve, and it leads to a solution space that most people don't end up exploring. That's what makes it fun. So if you really want to have fun with distributed systems, find yourself somebody who's building some really weird distributed systems problem, and then come at it and say, okay, I got the basic tools. How am I going to use those tools to build something that will make people's minds melt? So in Calvin, they had deterministic ordering. In Spanner, they have 2PC doing cross-sharding replication. In Spanner, they Paxos replicate their coordinator. Here in Calvin, they have a sequencer, which is Paxos, and of course they replicate that. The latency here per transaction is where it becomes interesting. They pay two PC round trips, so they have to go back and forth. All the messages we saw in that flow. Then in Calvin, all they have to actually do is the sequencing and the execution. So in some ways, it's simpler because there's fewer messages flowing back and forth. Aborts here, those are natural. You just simply vote no. Here, the problem is there isn't an abort model. Calvin doesn't allow you to say no retrospectively. You have to pre-declare everything you're going to do. Nice way to solve the problem. Spanner actually allows interactive transactions. Calvin does not. In Calvin, you have to define everything that needs to be done in order to make this happen atomically up front. This is in essence a write-ahead log model, where you write everything to the log before you commit the transaction. But in Spanner, it was more like what you needed for a SQL database, which was somebody starts a transaction in SQL and they might not know exactly what they're going to need before they get to the end. Spanner only blocks if a Paxos group fails. When the Paxos groups start failing, that means you have multi-node failures, then things will stop. So your availability is pretty good, and you still have strong correctness. In Calvin, the only time it stops is if the sequencer actually fails. That's why you replicate it. But, so the big thing I think in Calvin's case was, if you know everything that you need to know in advance, Calvin is probably a better solution. If you're trying to solve a more general problem, then Spanner might be the better solution. So when we look at the design space of this, Spanner comes out somewhere here in the 2PC Paxos space. Calvin is somewhere up here. 2PC has this failure mode where it's not, the throughput is okay, the flexibility is okay, but it's not great. Calvin has really good throughput, but is less flexible because you have to know what things are up front. And then Spanner is lower throughput than Calvin, but more flexible than Calvin. So you're moving through that space. You know, when I looked at this picture, I said, oh, that looks pretty, but I think I need to move those blocks around a little bit. All right, so let's look at this side by side. In two-phase commit, we have a coordinator that does a prepare. The participants who say yes. If the coordinator crashes, the participants are going to hold locks and wait until someone manually fixes the problem or the coordinator comes back. The decision is stored in that one place in the coordinator, and there's no alternate path. In Paxos, the proposer can crash, and we have a clearly delineated recovery protocol. This is how Spanner fixed their dependence on that two-phase commit coordinator. All right, so the question now is, if you're running Spanner and you get a cross-shard transaction that's stuck, where do you go looking for the problem? I mean, being good distributed systems people, you've got lots and lots of logging in there, so you're going to go look at logs. Question?
Yeah, I'm still confused for slide 25 for the Calvin. And we have deterministic order with Calvin. Why that has the highest flexibility? What's the difference between that?
No, Calvin has lower flexibility.
And another, what is the right side?
Well, this,
Yeah.
that's why I said those probably should be not where they are.
I see.
Yeah.
And why do we have, like, which company is using Calvin? Because we know Google is using Spanner.
Well, Google was using Spanner. I don't think Google uses Spanner anymore. A lot of these systems end up getting rewritten and changed because they learn things when they build them. I'm not sure that anybody's using either one of these systems at this point because Spanner's, what, 15 years old, something like that.
We are Linux. We are not using it.
I'm sorry?
Like, why don't we learn more, like, our current method?
Well, because we don't know what they are.
Wait.
If you want to actually learn what those are, then you have to go work at Amazon, or you have to work at Google, or you have to work at Microsoft, because they don't tell people. That's why these papers are so interesting often, the industrial papers. They don't tell you exactly how they did things, but they give you a vague general idea. But they consider the details of what they did proprietary information. There's a whole argument in academia on whether or not those papers really do contribute. And often with what they contribute is an understanding of a general approach to the problem. They don't give you something that you can go and you can download a repo and you can like build and start using. Because Google, Microsoft, Amazon, IBM, Oracle, any of the people building these large cloud infrastructures, this is a huge part of the actual value in their systems, is specifically how they solve those problems. So I'm using them as examples to explain different spots in the design space. And the design space hasn't really changed dramatically. You know, we've spanned 20 plus years of different approaches here. I mean, that's a really good question, and I appreciate the opportunity to try and frame that in context. I don't think I've seen any recent, I'm trying to think of when the last time I saw a good distributed consensus paper that was from industry, and I don't remember seeing one recently. Most of them are now more than 10 years old. And some of that might also be because they're not coming up with brilliant new models. They're mostly just improving existing models. They're building them better. Let's see, so Spanner uses Chubby and it uses True Time, and because we didn't even talk about block management. Chubby is a distributed block manager. So when you're doing distributed coordination, one of the things you often need to do is coordinate what's locked and to build distributed block managers. Distributed block managers have been around since at least the 1980s, when Digital Equipment was doing clusters, hardware clusters. They literally used, one of the very core things they built was a distributed block manager that ran across a cluster of different computers with shared resources. And they would block manage who owned what resource. And it was a recoverable DLM. So it meant that if a node failed, you could recover its resources and someone else could take over. They were building fault tolerant systems. And what's weird about that is it's not that different than what we're talking about here at a software level. It was just that in the 1980s, they were doing that on hardware. It was a software-mediated, hardware-assisted coordination protocol. And now what we mostly see are software-assisted, software-managed. We don't see hardware involved very much anymore. You do still see it sometimes when you're looking at very high-end scaling of systems. For example, anybody seen the Mac Studios? They're like $12,000 or $14,000 for a 512 gigabyte Mac. And people take up to 4 of them, and they put them in a cluster. What that literally means is that they take Thunderbolt connectors and they connect them to each other, and they form a fabric. And they do coordination over the fabric. And that is a distributed system. When I started looking at that, it was interesting because Apple doesn't explain how they built that. But other people have built systems that are using the same hardware technology, and they do describe it. And it's very consistent with how Apple uses and what Apple does expose. So again, this is an example of what happens sometimes, is that they have a very interesting high-speed coordination protocol that's running over one of the highest external buses that's available right now, and we have to figure it out by observing it externally. And in industry, you'll have to do that sometimes. You'll have to figure out what other people did by looking at a black box and trying to infer how they could have done that based upon what you observe. That's a fun job, too. It's a hard skill set to master, though. It's a skill set that requires that you come up with theories and make sure that you don't become wedded to the theory. It's very easy to think that you're very clever, you figured it out, and then what happens is you fall into confirmation bias. Does anybody know what confirmation bias is? It's the tendency of humans to see evidence that supports their position in a favorable light and to ignore the evidence that suggests that their position is wrong. When you're doing engineering work, when you're doing academic research, when you're doing anything in the real world, it's a very good practice to make sure that you are always looking at your own assumptions and saying, am I just seeing what I want to see? Or am I seeing something that is really there? Somebody came by office hours yesterday and asked questions about their project, and so I did a trick, and I think I might actually do that as a demonstration here because we're pretty much at the end of the material anyway. So I did what I will be doing. You guys can't see that. That's great. So who's willing to let me look at their repo? You don't have to. I mean, I was just going to show you exactly what I will do with repos after a week from Saturday. What I'll start by doing. It's not the only thing I do. Okay, well then I'll show you mine. I will take one of my repos and show what I do with it. Let's see, what is a good one to look at? I don't even have that one. Sorry?
Your agent workflow, your agentic workflow.
Well, I was going to put it on the screen in a second, but oh, I can't actually see it if I do that. Okay, fine. I'll take a random. Okay, it's going to make this hard, but we can fix that. Interesting. Did I not push it? Could have sworn I had, but let me go look. Oh, you know what? It doesn't matter. How about this? Because I know Arbiter's been changing. All right, well. It just keeps it from being annoying and asking questions over and over again. And no one can actually see this at home because the screen is not actually. Let's see. Oh well. So that's what they don't get for not being here. Actually, it's good afternoon. It's very important to use the correct thing with Claude, right? So I get a new code base. I'm like, I don't know what this does. One way of doing this is you can actually ask for an explanation of the code base. When I take something and do something wilder, I say, just send some agents out and tell them to look around and see what they see. It's literally unguided search. And the AI will push back usually against this because they say, it's not useful. I've had so many times where it says, I'll do it, but it's going to be kind of useless. And I have yet to find it not useful when I'm looking at projects. So this could easily take, 3 to 5 minutes. But the point is that when you give me your code base, this will pretty much be the first thing that I do. Claude's going to give me back a list of what you've done that's interesting. It's going to say, here are things that look interesting, but I didn't explore further. You can actually use that feed in again. You can say, now use that as a map for the next iteration. It's like you send little scouts out and they go and they look at parts of things. They don't have time to look at everything. They come back and they give you a map. Wow, I did a really exhaustive one here. This is more than it was doing yesterday when I was doing this during office hours, so this is fun. I have used this to search through my own work. Where when I finished my dissertation, about 6 months after that, I went back and I said, okay, I know there were a bunch of things that didn't make it in, but I thought were pretty interesting ideas, so, go through and look at it. And that's literally the case with Claude's. I don't think this is going to be very useful. I said, no, go ahead and do it. Look through the Git repo, through the Git history and whatnot. And what did they come back with? A list of 17 things that had been omitted that were interesting for potential future research topics. And Claude was like, wow, this is surprising. And it's partially because they're trained that undirected search is generally not very useful. I find exactly the opposite. You can use this in a more focused way on your own code base. You can say, what am I missing here? Or, how about my documentation? Does my documentation make sense? Look for coherency in it. When you start building distributed systems, Claude builds really good TLA plus specs, way better than I can do. That doesn't mean that they're necessarily correct. You do have to actually cross and check them. So all Scott said that the largest, most architecturally central module, format sensitivity paradox. It did very guided research this time. So I would probably go back and say, no, too focused. Or alternatively, and so I look at this, and now you can actually see what is here. And what's fascinating is that when I left this morning, it was, I apparently haven't pushed it recently, I swear I had, but the findings were even different than what it's reporting here. So this is whatever's in the current code base. It's not whatever I was working on. And every one of the LLMs uses all of the coding agents. They get what's called a system prompt, which is basically like a set of instructions on what to do and how to interpret things. And Claude's is probably by far, well it is, there's no question, it is the most extensive. It's like 25,000 characters. It's very long. And it contains things that are contradictory. So in one place it says do this, in another place it says don't do that. So the interesting question became, how does it decide what to do? And in the case of Claude Code, it's very interesting because you have different models you can choose from. And the models are explicitly trained differently. So they represent price tiers. OpenAI isn't quite as clear when you use Codex what you're trading off as you go across the models, but it is some of the same thing. Their system prompt is smaller. In the Claude case, what we did was I mean, we built a whole history of this. You can scrape them. They're all NPM packages. You can pull the NPM packages out. You can scrape the system prompts out of the distributed images, and you look at them and you say, how do these things compare to each other? What is the evolution over time? And nobody's really looking at this. And what was most interesting was when we started doing ablation studies. Does anybody know what an ablation study is? Okay, I have a list of 100 rules. They have conflicts in them, they have structure. The order in which I present things can change how things are interpreted. So in an ablation study, what you do is you start removing things and see how behaviors change. If you really have 100 things, I think we only have 27. The problem is that 27 factorial is a really big number. So it's not computationally feasible to search that whole space. Turns out someone else, a couple of people in different research areas, in completely different fields outside computer science, have actually done studies of how you do analysis of cross-factor interactions without hitting that combinatorial property. So the naive thing is just simply do the whole thing. And that's a power set. It's not even 27 factorial. The power set is 2 to the 27th, which is 2 to the 7th is 128. It's 128 million different combinations. It's a lot. Probably wouldn't be able to do that in 15 minutes. It's a lot of LLM calls too, because these are using LLMs to do the analysis. But it's criticizing the code. I love it. No type checking, linting, coverage metrics, or pre-commit hooks. This is why you have to be careful. I just typed that prompt in. When I do that, I will use the exact same prompt. It's still going to give me variations. But it will give me a map of your code, and it will tell me what's interesting about your code. And what I tend to do then is I tend to say, okay, well, it might tell me that things are working or they look good, and I'll just take that at face value. And what I'm going to probe at is when it says there's something wrong. Now I'll go look and say, okay, it says this is wrong. Let me go look at that, make sure, because I'm trusted. And if I look at the things that it says you did right, and it's not correct, I'm like, well, you know, I'm not biasing it against you if I ignore those things and just give you credit for it. But when it says you've done something wrong, then I can actually look and I can point to those pressure points and I can actually poke at it and say, what's going on here? So this is interesting because Claude actually ended up doing directed search. So I'll push back on Claude. You're absolutely right. Yeah, of course, Claude. I know, because you've done this kind of thing to me before. Undirected code-based scouring. Using kinds of techniques when you have an unknown code base can be quite helpful because they can scan through code and they can find patterns. That's what they're really, really good at. They can find patterns far faster than you or I can. Well, maybe you're really fast at it. I can't do that. When I pick up a 500,000 line code base and I start looking at it, the first thing I'm like is, oh my gosh, this is kind of overwhelming. And what I need is I need to have that nice document that everyone should have written and no one does for their code base going, this is how you get started with this code base and here's where everything is. And it's not fair to say no one does that. I have seen code bases that are like that, but they're rare. Much more often, the documentation is wrong, out of date, inconsistently written, scattered around. Oh, look, there's 479 README files in this repo. What am I going to do? I see undirected means that it's just poking at things. It's just looking around and saying what's there. It's not actually looking for something specific. This is why I looked at that and I laughed, because I got comments on the fact that the Python code that Claude writes is crappy. Yes, I know. It doesn't use good styling. It often tries to be Python 2.17 compliant. I'm joking on that, but it does feel that way. It's very hard to get it to work consistently. How many of you are using an AI coding agent to assist you? 2 people. That deserves cookies. There you go. Now everybody else is going to be like, I'm using one too. Let's see. The undirected scour, very different from the directed ones. What caught its eye? The gap between vision and implementation. 5 rules exist in code, but the scourer discovered 152 findings across 100 plus categories, like unbounded trust delegation, ghost feature, recursion hazard. That scourer data is sitting there dormant, no rules corresponding to it. Classifier bugs are the interesting part, not the findings. The 160 sample human audit found 12% disagreement. The 3 systematic bug classes, empirical, the 160 samples. That was me going through 160 examples. But we use that to calibrate. Is the 5 rule versus 100 categories gap deliberate, minimalism, or unfinished reconstruction? If models resolve contradictions stochastically, what grounds the promise the higher tiered contradictions? So now I actually have things to go look at, as opposed to before, where it's like, I don't really care that your Python code sucks, because everybody's Python code, almost everybody's Python code sucks. My Python code is bad. And I try to use all the modern things and use annotations and so on and so forth. But research project in the middle of a phase transition. I should have pushed it. I swear I pushed it. It's been actually coming up with some really interesting results, which is what's fun about it. One of the things that came out of this work was I found an actual bug in Gemini CLI. And I have an outstanding bug fix for it, which is kind of a nice story because it will teach you the other problem of AI coding assistants, namely, there are 678 outstanding PRs against Gemini CLI, of which 270 of them, I think it was, are P1s. And the one that I want is, in fact, listed as a P1 because it basically just loses information every time it goes across the compaction boundary. And the infrastructure is all there. We found it from looking at the system prompt and going, oh, and then traced it into the code and said, the code's not actually representing this correctly because the schema is missing a field. So they literally collect this data and then throw the data away. This is one of the things they're getting very good at finding these kinds of bugs. I don't know if anybody saw, but they're now actively using, like Claude, for example, to do security scans, and they're finding real bugs in systems. Have any of you ever heard of Donald Knuth? He wrote this thing called The Art of Computer Programming. I think he's working on volume 4C or 4D or something right now. He's in his late 80s, and how many of you have ever used a web browser? You're not getting a cookie for that one. Well, maybe get one afterwards, that's fine. HTML, the language we use for describing web pages, was in fact a derivative of TeX, which you might have heard through LaTeX. Some of you might have used LaTeX. LaTeX Knuth specifically gave us several things. I would say he gave us programmatic visualization. So you could literally create visualizations through programming languages, and that turned into HTML. It went from TeX to SGML, structured graphic markup language, to HTML, hypertext markup language. And the other thing that he gave us, interestingly enough, was scalable fonts. He got really annoyed. So he's a mathematician, and he said it's really annoying to do write mathematical text and get them typeset and printed because the fonts aren't uniform and getting mathematical notations done right isn't uniform. So of course tech is really good at doing mathematical notations. We still use his formal mechanisms for describing formulae and whatnot up on web pages. It's called MathJax. And scalable fonts today are the basis of TrueType and OpenType. So the idea that a font is in fact nothing more than a function that describes what a character looks like. And since it's now a function, you can scale it up and down ad nauseam. Before that, there were always rastered images, and those don't scale very well. At any rate, so he recently noted that he had solved an open problem in Hamiltonian paths, which is a way of walking through graphs that has real applicability in computer science. And he did that because Claude figured out how to solve the problem in a specific example, and he took the example and he built a full proof of the general case. So I thought that was fun. So these things are actually really being used. And I'm going to wrap it here because I think that we've accomplished what I was hoping to accomplish. And, right. So we got logistics at that point. Did you want your cookie?
No, I'm running for class.
Well, what was that? What is it that's so noisy in those doors? It's like so weird. All right, good. Okay. I still have a couple of cookies left if anybody wants a cookie. Is it okay? Everybody's bundling up for the lovely weather.
Oh, wait, you want some?
I'll have all. Thank
Oh, is it actually helpful?
you. Yes, I made it this morning. It's not quite warm, but. No. He's greedy, isn't he?
No harm in asking.
Fair enough. Lisa, may I have another?
Thank you.
You should not bring it next class and bring it to class after. So that, like, no one will trouble.
You can never be predictable, otherwise. Did you get one?
Yeah.
Okay, I thought so, but I should probably stop the recording too. Because otherwise, those people are going to be all jealous of the fact that they didn't come and get cookies.
I just want to double check. Is there oatmeal in the cookie?
No.
Okay.